Okay. Okay, so it's a pleasure to introduce me Sungwon An from Roosevelt University. He's going to go to talk about maximizing path on the forbidden subgraph in extremal combinatoric, and it's part of the undergrad faculty program in Park City Mathematics Institute during the summer of 2025. Thank you
Uh,
for being
mhm.
willing to talk, someone.
Oh, thank you. Thank you for giving me this opportunity to talk. Um, so instead of giving you a bunch of result and um, complicated mathematical formulation, for the undergraduate, I would like to give some small lecture. Um, it could be too easy for faculties, but hopefully faculties get some learnings too. So before I mainly talk about extremal combinatorics, let me give you some background. So I want to introduce this graph. I'm gonna call that G. Okay. And this G is consisted of vertices and the edges. So V here is called the vertices, and E is a set of edges. So if I give you a simple graph, there will be a vertices, and then there's some edges between them. There could be no edges between some vertices, or there could be one edge between vertices. And also I'm gonna make a notation for the number of vertices and edges. I'm gonna put this absolute sign V, that means the number of vertices, and the absolute sign of E means the number of edges. So that's basically whenever I put the absolute sign, I will mathematically we call that magnitude. When we put this absolute sign, it will be the number of something. And also there's one more extra notation. Suppose here is the X, and here is the Y, let's call that. Then this is the X is the vertex of this, and Y is the vertex. Okay, it's vertex. And D of X is called the degree of X. And these are the number of edges coming out from the vertex X. So for example, here, dx, in this case, there are 3 edges, 1, 2, 3, right? So dx is equal to 3. And for the dy, will be, here's 1 and here's 2, okay? So there are 2 edges. And whenever I talk the edges, those edges are not directed, they're undirected. It just tells you which vertices are connected. It doesn't tell you which direction. They're all undirected. There is some graph theory with a direct edges, but we don't have any directions from there. And also one more background is the type of graph. So there's a few, there are many types of graph, but I will talk about a few of them. So the types of graph. And the first one is the complete graph. And I'm going to denote that by KR. And R is the standing for the number of vertices. So for example, if you have, let's say, 4 vertices like this, then the complete graph will give you the, complete graph will give you the edge to all vertices. Okay, so there's no non-edge between some vertices. All vertices have an edge between there. And this is the example of K4. Okay. And another one would be complete bipartite graph. Complete bipartite. I'm gonna denote that by KST. Okay. So what is KST? KST is so suppose you have a here you have a S vertices, and here you have a T vertices, and this group of S and group of T, they do not have edges, but between those S vertices and T vertices, they're completely connected. Okay, like this. And then one more thing that I can give you, and there are many more. There's cycles, there's stars or things like that, but I want to focus on just these 3. So the third one is a path. And I'm gonna notate that by PR. R means the number of vertices. So here are R number of vertices. And then they're connected like a path. Okay. And that's called a PR. So I would like to ask one question here to the audiences, to everyone of you. Suppose your number of vertices is n, then what is the maximum edge? What would be the maximum number of edge? Can anyone? So you have n vertices. What would be the maximum amount of edge that you can draw?
And to the end?
So
there's only one edge between any 2 vertices. That's
right.
Yeah.
So it's like the handshake problem.
Yes. Well, actually, yeah, it's n choose 2. Because you're picking up you're picking up 2 edges or 2 vertices, and you connect one edge, and then you pick up 2 edges or 2 vertices, and you connect edges, and by doing that, the number of edges will be n choose 2, and approximately this is n times n minus 1
over 2.
over 2.
Yes.
So that will be approximately n squared over 2. So that's the approximately the number of maximum edges you can draw in n vertices. The mentor in 1907, he gave a interesting result. So here is a theorem. It was Mantel, sorry, not Mantel. Mantel from 1907. He showed that given this n vertices, there are n number of vertices, the maximum number of edges with no triangle edge is, it must be smaller than n squared over 2, right? Because, well, if you have like complete graph, then you should have like edge from here, that's triangle, and there is an edge from here, those are the triangle, and there's so many triangles. But we would like to have the Mantel actually show that maximum edge with no triangle, this kind of a triangle, is not n squared over 2, but n squared over 4. This can be proved by induction very easily. So here's a proof. Is that suppose this is true for anything less than n. Okay. And let's say this is an induction proof. So suppose this is true for any n, less than n. You pick two vertices that has an edge. I'm gonna call that x and y. And there's an edge between there. And there the rest. There's n minus 2. N minus 2 vertices. And because of this induction, we can tell that the maximum edge without triangle in this n minus 2 vertices should be n minus 2 squared over 4. That will be the number of edges. And also there's one edge here that's equal to 1. And then there's the edge connected between this set of xy and this n minus 2 vertices. But when they do that, this x and y should not have a common neighbor, right? If they have a common neighbor like this, then now they have a triangle shape. So they should not have common neighbors, but still should be maximizing the number of edges. So that means there should be n minus 2 edges at max. If it is more than n minus 2, then there should be common neighbor from x and y, and you get a triangle. So now if you count those, then the maximum of edge, number of edge, is 1 plus this one, n minus 2, and plus this one from the induction, n minus 2 square over 4. I should put this as a inequality. Okay. So if you add this one algebraically, you expand this and add and things like that, it will definitely show that it should be n squared over 4. Okay. And this is sharp. Actually, this one is sharp, that the number of edges, the maximum edges, should be n squared over 4. This is without triangle. Okay. And there is a perfect example of where this maximum edge occurs. That's the bipartite, complete bipartite graph. So if you have here n over 2 vertices, and here's another n over 2 vertices, and then you draw the complete bipartite graph like that, then the number of edges here will be n over 2. There's n over 2 times n over 2. So that will be n squared over 4. So it's not just the upper bound. N squared over 4 is not just the upper bound, but this is the sharp bound. So this kind of actually study is called extremal combinatorics. So here's actually, let me write down the some definition. It's a partial definition. So extremal combinatoric is find maximum number of structure. In this case, this was the edge, but it can be other things. Maximum number of structure when a subgraph H is forbidden. In this Mantel's theorem, the subgraph H is the triangle. So the Mantel's theorem is basically find the maximum edges when the subgraph triangle is forbidden. And there's a notation for this, the number of structure, number of edges. The notation is EX, N means the number of vertices, and H is the subgraph that is forbidden. Okay, so this is the maximum number of edges with no H. Okay. And the Mantel theorem would be they found EX over N and triangle. Well, triangle, you can call that as a K3. K3 is also the complete graph with the 3 vertices is also the triangle. Or you can say as a cycle, 3 vertices of the cycle. This is equal to n squared over 4. Okay. And there's some further research after that. So there's another theorem.
Yeah. Sorry. I mean, when you say it's not a fixed subgraph, but a fixed type of subgraph.
fixed
For instance,
types of, yeah,
angles in this case, or squares, or
that's right. That's right. Yeah, it could be squares, or it could be star, or it could be path,
but
or
it's
things
not a
like that.
fixed one, but it's a type of graph.
That's right. That's right.
Okay.
Mhm. So there is a theorem, the further research after that. So here's another theorem. It's from the Turan in 1941. And he found the maximum edge with no complete graph in KR. KR was the complete graph, right? That's all vertices with the V equal to R, right? The complete graph. And the extremal number of this complete graph with the R vertices is 1 minus 1 over R minus 1 times n squared over 2. Okay, so we still have this n squared over 2. This is the maximum number of edges on the complete graph, but then you have this fractional amount to avoid this KR complete graph. And later, it's a Kovar, and Sos, and Tra, 1954. They found the extremal number of the complete bipartite SNT. So this is the number of maximum edges without this complete bipartite graph. It was n to the, I'm gonna write O here, and the n to the 2 minus 1 over s. So in the complete graph, if you want to avoid the complete graph, it will be the fractional amount of the maximum. But now you have some losing powers with this
It's
complete
independent of
bipartite.
T. It's independent of T.
Oh, yeah, it's a good question. So it's not dependent on T. It's only dependent on S. So it's independent of T. So even if T is like infinity, you still have this order.
But could you repeat what KST is?
Oh, yeah, sure. So that's you have here S number of vertices, and then here you have a T number of vertices, and then they are completely connected. They're completely connected, but among those S vertices and among those T vertices, they are not connected. That's why it's complete bipartite. It's bipartite. So the number of edges should be n to the 2 minus 1 over s to remove this kind of graph in your entire graph. Okay. So there are many more studies, like there's like a cycles or even stars or paths or things like that, and then there's a lot of non-n square order, but I'm not gonna talk about it because that's not my main talk. So that's the background, but recently, now in the past 10 years, I say, people are more interested in this generalized Turan number, and I will explain what that is. So the generalized Turan number is the extremal number with n vertices, but now this time we are not counting the maximum edge, but we are counting maximum some subgraph f, given that another subgraph f is forbidden. So in other words, this is the number of f, maximum number of f with no h. And what I discussed before was the special case. The special case is ex of n and k2. K2 is just one edge, and h, that is just a extremal number of nh. Okay? But this is much generalized. We are not only looking at the maximum edge, but we want to find the maximum number of this subgraph f in the n vertices graph. There are many works on when h is KST, okay? Complete bipartite graph. So H is this forbidden graph. And here are some past works. So past works is that the first one was it's Alone and in 2016. It's all like combination of works. Ma and Yuan in 2018, and Bayer and in 2019. What they did was they found the number of complete graph with this no KST. So in other words, the extremal number of KR. So it's a maximum number of KR complete graph when its KST is forbidden. And of course, the R has to be, no, actually, it's a case by case. And this one is actually equal to or less than equal to order of n to the r minus r times r minus 1 over 2s, okay, when r minus 1 is less than equal to s and less than equal to t. And also it's less than order of n to the s plus 1 over 2 when the s is less than r minus 1. So so they found this number of complete graph, and there are some more for the other cases, but I don't want to write that down. Also in along the same group in 2016, they found the number of complete bipartite, the smaller complete bipartite given that the bigger complete bipartite is forbidden. So it's N, K, A, B, where this A, B is much, much smaller than S and T, and K, S, T is equal to, or actually less than equal to, order of N to the A plus B minus A times B over S. And also there's another group recently, Gardner and Palmer in 2019. They found the number of paths in a very specific case of the complete bipartite. So they found the extremal number of paths in R. So there's the R vertices with a path, and K 2T. So it's not generalized one. It's not KST. It's a K2T. And then less than equal to order of N to the R plus 1 over 2. Okay.
Someone,
So,
but for the
Mhm.
case 2, I mean, you say A and B are much smaller than S and T.
That's right.
So, but you are avoiding KST in your graph, right?
That's right. That's right.
But if S and T are bigger than AB, that's always the case because you have less point in AB. I don't know.
Well, so for example here,
Probably I am understanding that completely wrong.
no, here is a S and here is a T.
Yeah.
And if these are forbidden,
Okay.
well, the small a and small b can be completely bar type, but these may not be connected. So you still have a KAB, even if KST is forbidden.
Okay.
Does it make sense?
Yeah.
Yeah. If A and B are greater than S and T, then there's no extremal number. But if KAB is smaller than ST, then there is. So here is an open question. That is not proved yet. Is what is the extremal number of PR of KST would be? Okay. So here we have a specific case when S is 2, but what would be in general S? So I went to this Park City thing, and then I was thinking about how to, well, there are a lot of other open questions, but I was kind of hooked into this question because I thought I was able to do it. And then I found like very small, tiny proof. I should say it's a tiny proof, tiny theorem. And then I was able to find the general KST for the P4. I should say it's on 25. The number of P4 when complete bipartite KST is forbidden is actually equal to or less than equal to the order of N to the 4 minus 3 over S. Okay. And in fact, it's easy to prove that. So here's some note. It's easy to prove that the extremal number of n p3 case kst is less than equal to order of n to the 3 minus 2 over s. So this is very easily proved, and I kind of extended the knowledge to prove this P4 cases. And the conjecture that I have is that you see the pattern. So the extremal number of PR, the number of paths, I mean the size of passes PR of KST is less than equal to the order of n to the r minus 1 over s. Okay, that's my conjecture. And I think that's true based on the few result. And I know how to do P5 actually, but I didn't go that further because I want to maybe like look into PR, the general case R, rather than the specific cases. But let me actually give you some small proof of why this is true. I don't know, like I was just skim through it. I have only like less than 20 minutes. So there are two lemmas to prove this. So here's lemma 1. Is suppose G is KST free. Okay. In other words, the graph do not have a complete bipartite of one side S and another side of size T. Then we have this inequality. The sum of X in the vertices of degree of each vertices in V choose as is less than equal to the order of n to the s. And the idea is kind of simple. So I'm just gonna write down the idea here. This idea is you count the number of k as 1. Okay. So count number of k as 1 from the head, from S head, and from one tail. Okay. So here is how we count the number of k as 1. So the first one, the number of k as 1 from head, S head, is less than equal to. So for example, you have if you have x1 through xs, okay, then the maximum amount of neighbors this S head will be maximum amount will be t minus 1. Because if they have a t neighbors, then that will be a KST. And that will be complete bipartite. And you cannot have that. So it will be maximum of t minus 1 and not more than that. So the number of k as 1 will be it's bounded above by the number of these choices, and then they each have this set of S vertices have a t minus 1 neighbors. And this is n choose S times t minus 1. And that will be order of n to the S. That's coming from here. That's coming from the right. That tells you the right hand side. On the other hand, if you count KS1 from tail, one tail, then this is equal to the each vertices x in V, each vertices should have S, it's bounded by, actually this is equal to the degree, the degree of x, that's the number of edge going out from the x, and then you choose S from there, because the other side is S. So it will be degree of x, because here is the x, and then you have a degree, and then you choose S among them, and that will be counting the KS1. So here you have a 1 equal to 2, and this is 1, and 2 is that, but it will be bounded above by the order of n to the s. So you have this equality. And here's a corollary, actually. That's what I'm going to use. Is that with a little bit of modification, it's not hard to show that the sum of each vertices of the degree of x to the power of s is going to be less than equal to the order of n to the s. Okay. And here's a second lemma. I guess the time is running out, so I'm just gonna write down the result. Here's a second lemma. Is that the number of P4, the number of paths is actually bounded by degree, or the sums of the vertices with the degree of x to the power of 3. And you can show that using the graphical representation, and then you count every single P4s from each things, and there's some lot of technical details that I should write down, but I'm skipping here. So I'm using these two things as the tool. So the theorem here, now we are going to the proof of the theorem. Is so you start with the P4, and that's bounded by the sums of x, each vertices with a degree that is squared, that is cubed. But then here I'm using the Holder's inequality. I don't. It's not, maybe the undergraduate students are not familiar with this inequality, but it's very, very, very efficient tool. So here's a Holder's inequality. So let me just generalize the theorem, the inequality. So if you have a sum of an times bn, the series is in n. Then this is equal, or this is bounded and above by the following. Sum of an to the power of p of 1 over p, and then times sum of, by the way, these an and bn's are positive. They are all positive. And bn to the power of q and 1 over q. Okay? But there's a restriction on p and q, is that 1 over p plus 1 over q has to be equal to 1. And this one is same for the integration, not just sum, but also integration. So I'm going to use this Holder's inequality here. So that will be, so here you're missing, there's a 1 times that. I'm gonna, you can think of that as a an and this one as a bn. Then it will be less than equal to sum of those p times 1 to the p and times to the power of 1 over p, and then sum times d of x to the power of q, and then 1 over q. I did the exactly same thing. I just let an to be a 1 and bn to be a dx to the power of 3. And here we know that this is n, right? That's the number of just 1 to the p is 1. This is just the number of vertices. So this one is n. Oh, and one more thing. I gotta put 3 here. There's 3 missing. The 3 times q. And for this, I need to choose a q in a way that this one is similar to that. And the way to do it is I choose, so here I choose q equal to s over 3. And here we have a restriction that s should be greater than 3. So I should write in the theorem, what to write here, s is greater than 3. That's one of the conditions. S is greater than 3. Then 1 over q is it's reciprocal, so there will be 3 over s. And then 1 over p, that's 1 minus 1 over q. 1 over p is 1 minus 1 over q. It will be 1 minus 3 over s. Okay. So if I use that, now this becomes, so you have a p4, and then replacing q and p, and 1 over p and 1 over q. This is what you will get. It will be less than equal to n to the 1 minus 3 over s, and then multiply by this one is summation of dx to the power of s, and then 3 over s. Okay. And then from lemma 1, here's lemma, actually from corollary, we have that this one is n to the s, so from corollary. So that means this is bounded by n to the 1 minus 3 over s times n to the s and 3 over s, and that's equal to n to the 4 minus 3 over s. I should write O here. Should write O here. Because you got to bound that by some large constant. This one has this is a c times into the s, and this c is very large. So you have that. Okay. So that's it. And the further study would be, as I mentioned here, it will be conjecture that you want to bound that by n to the r minus 1 over s. So yeah. So any questions?
And why you cannot prove the general case? What is the problem with this argument that you just gave us for 4, I'm sorry.
Oh, you mean why is it hard to generalize this P4 to PR?
Yes.
Oh, it's because so the one that I did is I didn't show you this in detail.
Mhm.
This one. If you do like P5 and P6 and so on, this side becomes more complicated.
Oh.
And you can do it for P5, but starting P6, now it's out of control. Using the technique, I didn't show you the technique here because it takes a lot of time, but the technique that I used here, if you go beyond the P5, it becomes out of control. That's why I cannot generalize it yet, but if anyone can do it, that would be great. Yeah. As long as you get this one. This is the hard part. The rest is, I think, the Holder's inequality will give you the right bound of
Mhm.
P n to the r minus 1 over s. Oh, and one more thing. This is actually the case when s is greater than 3. So even this one is not completely proved, because what if s is equal to 1 and 2 and 3? How can we prove that? Well, it's not, so yeah, it's not proven yet. There would be another next thing that if people are interested, maybe they can do it.
Any other question or comment? Melanie.
Yeah. So one nifty thing about the number 3, a number bigger than 3, means that it's equal to 4 or bigger.
That's
So
right. That's
is
right.
that connection between your proof having like s bigger than 3 and P4 a coincidence? Or do you think if you had something
Oh,
like P6 or P7, you might get a theorem like this, but your s would have to be big too?
that's right. If you have a P5, so this is P4, and I
Mhm.
said I was able to do P5, but in that case, S should be greater than or equal to 5. So this number actually, the number of vertices determines how large S should be. And it's coming from the Holder's inequality. So here,
Yeah.
in order
Mhm.
to have 1 over Q less than 1,
Yeah.
you should have a Q S greater than 3, right? So this is the restriction that makes S is greater than 3. But if you know how to, if you can do the same result without using Holder's inequality, then you may able to do the case of the smaller one, S less than. So here I should say to R minus 1, and here is R S
Okay.
less than R minus 1.
So it's sort of like you've got this idea, and a method of proof using Holder would have this restriction, but there might be a method of proof that doesn't
Then you can do
have
that.
that
Yeah,
restriction. Oh, that's cool.
that's right. That's right. Yes. So, yeah, that is another good kind of thing that people can do.
Okay, any other question or comment?
Did you write up your proofs?
Oh, did I?
Yeah.
Oh, yeah. I wrote the whole proof. if you want to see, I can send you one. It's not
I'd love to.
it's not a problem. Yeah, yeah, sure.
Me too.
It looks cool.
Oh yeah, yeah, sure. I'll send it to Wilfred, when you can send out to
Okay.
all, yeah,
Let's do
everyone
it.
in this talk.
Okay, good.
Yeah, it's not for like publishing or anything, so I just did it for maybe like, that's why
Oh.
it's called a small theorem, tiny theorem. Anyone can build up something out of here.
Okay, let me stop the recording.